There was a time when the universe itself was cloaked in utter darkness, no stars, no galaxies, just an endless void stretching across the cosmos. This was the Dark Ages, a mysterious era lasting hundreds of millions of years, hidden from our telescopes and shrouded in questions. What happened during those silent eons? How did the universe transform from a featureless abyss into the glittering cosmic tapestry we see today? The answers lie buried in some of the most mind-bending theories ever conceived, each one more astonishing than the last. Picture this: a universe so young, it hadn't yet lit its first star. The only light came from the fading glow of the Big Bang, slowly being swallowed by the expanding darkness. Yet within that blackness, the seeds of everything we know, planets, galaxies, even life itself, were quietly taking shape. Scientists call it the cosmic dark ages, but it was anything but empty. Strange forces were at work, processes so bizarre they challenge our understanding of physics itself. Some theories suggest hidden dimensions played a role, while others propose the existence of shadowy particles that shape the cosmos in ways we're only beginning to grasp. Today, we're diving deep into 30 of the most extraordinary theories about this enigmatic period. From phantom energy fields to primordial black holes, from cosmic strings weaving the fabric of space-time to the possibility of entire universes colliding in the dark, every one of these ideas could rewrite the story of our origins. And here's the most thrilling part: we might be on the verge of uncovering the truth. New telescopes like the James Webb Space Telescope are peering further back in time than ever before, giving us glimpses of those lost ages. So buckle up, because by the end of this journey, you'll never look at the night sky the same way again. What if the Dark Ages weren't just an empty void, but a hunting ground? Some scientists believe this era was ruled by primordial black holes, ancient monsters born in the chaos of the Big Bang itself. These weren't the black holes we know today, formed from collapsing stars. These were primordial, tiny, fierce, and everywhere. Picture trillions of them, each no heavier than an asteroid but packing the gravitational punch of a mountain. They'd lurk in the darkness, devouring any matter or energy that dared to wander too close. And here's the chilling part: their feasting could be why the universe stayed dark for so long. These black holes wouldn't just swallow light, they'd reshape the cosmos. As they moved, their gravity would pull gas and dust into dense patches, like cosmic breadcrumbs marking where galaxies would later form. Some theories even suggest these black holes acted as seeds for the very first stars, their immense gravity compressing matter until nuclear fusion finally sparked the universe's dawn. But their most bizarre legacy might be hidden in the echoes of the Big Bang. Astronomers have noticed strange gaps in the cosmic microwave background, regions where radiation seems oddly faint. Could these be the fingerprints of primordial black holes, their shadows still lingering after billions of years? The wildest twist: some of these black holes might still exist today, drifting unseen through our galaxy. If they're out there, they could solve another mystery: dark matter. Imagine if the invisible glue holding galaxies together wasn't some exotic particle, but countless primordial black holes too small to detect. It's a theory that ties two cosmic puzzles into one, revealing how the darkest chapter of the universe might still be shaping our night sky. But the black holes weren't the only reason the early universe stayed so dark. Imagine stepping into a cosmic steam bath, a thick, swirling haze of hydrogen gas so dense it smothered every flicker of light. This was the hydrogen fog, a blanket of neutral atoms stretching across the entire universe, absorbing radiation like a sponge. For hundreds of millions of years, any light trying to pierce through this fog would have been instantly swallowed, leaving the cosmos in a state of perfect blackness. Scientists call this the epoch of reionization, and it's one of the most pivotal chapters in cosmic history. Back then, hydrogen atoms were everywhere, their electrons perfectly paired with protons, making them hungry for any passing photons. Ultraviolet light, gamma rays, even the faint afterglow of the Big Bang, none of it stood a chance. But slowly, something began to change. The first stars, colossal and blue-white, started flickering to life in the void. Their intense radiation blasted through the fog, stripping electrons from hydrogen atoms and ionizing the gas. It was like a cosmic sunrise happening in slow motion, a wave of light burning away the darkness one patch at a time. Computer simulations revealed just how violent this process might have been. Gigantic bubbles of ionized gas expanded around those early stars, carving tunnels through the hydrogen fog. Over millions of years, these bubbles merged, their edges crackling with energy as the last pockets of neutral hydrogen resisted. Eventually, the fog lifted for good, and the universe became transparent, a moment as transformative as the Big Bang itself. Today, we can still see echoes of this struggle in the light of distant quasars, their beams subtly altered by the last wisps of that ancient hydrogen haze. Here's what's truly staggering: without that fog, we might not exist. By blocking early radiation, it gave the universe time to cool and structure itself, allowing gravity to sculpt galaxies and stars. And when the stars finally broke through, their light didn't just end the dark ages, it set the stage for everything that followed. So the next time you look up at the night sky, remember, those twinkling lights are the descendants of the very first stars that dared to burn through the darkness. The universe's dark ages might owe their longevity to an invisible puppeteer, dark matter. While we often think of it as the silent scaffolding of modern galaxies, its role in those early eons could have been far more active. Picture this: trillions of dark matter particles, invisible and intangible, swirling through the primordial cosmos. But unlike today, where they pass through ordinary matter like ghosts, some theories suggest they behaved differently back then, slamming into hydrogen atoms, stealing energy, and putting the brakes on star formation. How? Imagine a game of cosmic pinball. In most models, dark matter particles barely interact with normal matter. They're like players who never touch the ball. But certain exotic varieties, like self-interacting dark matter, could have crashed into protons and electrons during the Dark Ages, absorbing heat and scattering light. This would have kept gas clouds too warm and dispersed to collapse into stars, stretching the era of darkness for millions of extra years. It's a twist that turns dark matter from a passive observer into the ultimate cosmic delay tactic. The evidence might be hiding in the cosmic microwave background. Tiny fluctuations in this ancient light could reveal where dark matter's friction left its mark. Some researchers even propose that dark matter's interactions created bizarre, dark atoms, shadowy counterparts to hydrogen that clumped together in their own invisible structures. If true, the early universe wasn't just a battleground between light and dark. It was a double-layered cosmos with two parallel histories unfolding in the same space. Today, scientists are hunting for these rogue particles in places like the Large Hadron Collider and deep underground labs. When a detector's crystal suddenly vibrates without explanation or a particle collision spits out missing energy, it could be a whisper from the Dark Ages. Even more intriguing, if dark matter's influence varied across the universe, it might explain why some regions lit up with stars earlier than others, like patches of a forest burning away fog at different speeds. The most mind-bending possibility: dark matter might not just have prolonged the Dark Ages, it could have shaped the very architecture of the cosmos we see today. Those early interactions might have nudged gas into the filaments and voids of the cosmic web, setting the stage for galaxies to form exactly where they did. So while we still can't see dark matter, its fingerprints could be etched into everything from the oldest light in the universe to the spiral arms of our own Milky Way. What if the Dark Ages weren't just a quiet lull, but the result of a cosmic speed trap? Some theorists propose that dark energy, the mysterious force driving the universe's expansion today, didn't always behave so predictably. Imagine a sudden surge, a phantom energy spike ripping through the infant cosmos, stretching space itself so violently that light couldn't keep up. This wouldn't just slow the birth of stars, it would strangle their light before it had a chance to reach anywhere. Picture a rubber sheet pulled taut until it's nearly transparent. Now yank it harder so fast that any waves moving across it get stretched into oblivion. That's what might have happened during this phantom surge. Photons emitted by the first stars would have been redshifted into nothingness, their wavelengths dragged so thin they vanished from the visible spectrum. The universe wouldn't just be dark, it would be unseeable, as if space itself had turned into a hall of mirrors where light got lost in the stretching. The implications are staggering. Normally, dark energy works slowly, nudging galaxies apart over billions of years. But if it briefly went rogue, perhaps due to some exotic phase transition in the early universe, it could have stretched the cosmos thousands of times faster than today's expansion rate. Gas clouds ready to collapse into stars might have been torn apart before fusion could ignite, like a match snuffed out by a hurricane, even more bizarre. This surge could explain why some regions of space seem unnaturally empty today. The phantom energy might have left behind cosmic deserts, vast voids where matter was scattered too thin to ever form galaxies. Critics argue the theory stretches credibility literally. No known mechanism explains why dark energy would spike so violently only to settle down later. But supporters point to odd quirks in the cosmic microwave background, where certain patterns resemble the echoes of rapid expansion. And if future telescopes detect ultra-distant galaxies forming later than expected, it could hint at a lost epoch when the universe hit the brakes on star formation. The wildest part, we might still feel the aftershocks. If dark energy surged once, could it happen again? Some models suggest these phantom bursts could be cyclical, lurking in the fabric of space-time like a dormant virus. If true, the Dark Ages weren't just a one-time event. They could be a recurring nightmare woven into the universe's very design. The very first stars in the universe should have been impossible to miss, colossal, blazing giants hundreds of times heavier than our sun, burning so bright they could outshine entire galaxies. Yet when astronomers scan the deepest reaches of space, these cosmic pioneers are nowhere to be found. They call them Population 3 stars, and their disappearance isn't just a mystery. It could hold the key to understanding why the Dark Ages lasted so long. These weren't ordinary stars, born from pure hydrogen and helium, untouched by the heavier elements that fill modern stars. They would have burned at temperatures beyond imagination, their surfaces crackling with ultraviolet fury. Their short, violent lives ended in explosions so powerful they could have ripped apart the delicate balance of the early universe. Some theories suggest these supernovae didn't just fade. They self-destructed in hypernova, blasting their surroundings with so much energy they sterilized vast regions of space, preventing new stars from forming for eons. Here's the twist: their deaths might have seeded the universe with the very thing that kept it dark. When these stars exploded, they could have flooded space with dense clouds of neutral hydrogen, recreating the fog that blocked light for millions of years. It's a cosmic irony. The first stars may have inadvertently reset their own universe, plunging it back into darkness just as it was beginning to wake. But if they're gone, how do we find them? The James Webb Space Telescope is our best hope. By peering into infrared wavelengths, it might catch the faint afterglow of their supernova or spot the ghostly outlines of their remnants, black holes or neutron stars drifting alone in the void. Even more tantalizing are the heavy elements they left behind. Traces of gold, carbon, or oxygen in ancient gas clouds could be the fingerprints of stars that died before most galaxies even existed. The most haunting possibility: some of these stars might still be out there, hiding in plain sight. A few could have been just small enough to survive, lurking in the emptiest corners of the cosmos, their light stretched and dimmed by billions of years of cosmic expansion. Finding even one would rewrite our entire understanding of the Dark Ages, proving that the universe's first light never truly went out, just faded into the shadows. The cosmic reionization wasn't a smooth, uniform dawn. It was more like flickering streetlights struggling to pierce a thick morning fog. While the first stars and galaxies began burning away the hydrogen haze, some regions stubbornly clung to darkness, creating a patchwork of light and shadow across the early universe. This delay wasn't random. Hidden forces may have been at work, sculpting these cosmic shadows in ways we're only just beginning to understand. One clue lies in the cosmic microwave background, the faint afterglow of the Big Bang. Tiny fluctuations in this ancient light reveal where matter was denser or more spread out, and oddly, some areas show patterns that don't quite fit our models. These anomalies suggest certain pockets of the universe resisted reionization longer than others, possibly because they were drenched in extra hydrogen or shielded by vast clouds of cold gas. Imagine a sponge soaked in water. Some sections dry faster when exposed to sunlight, while others stay damp in the shade. The cosmic dark ages might have faded unevenly for the same reason. But there's a wilder possibility. What if dark matter played traffic cop, slowing down the process in certain zones? Some theories propose that where dark matter clustered more densely, its gravity could have trapped gas, keeping it cool and neutral long after neighboring regions had ionized. This wouldn't just create cosmic dark spots, it might explain why today's universe has such a lopsided distribution of galaxies. Those stubborn pockets of darkness could have stalled star formation, leaving behind vast voids where matter never fully coalesced. The James Webb Space Telescope has already spotted hints of this uneven reionization. Distant quasars, brilliant beacons from the early universe, sometimes cast shadows, their light absorbed by lingering hydrogen fog billions of years after most of the cosmos had cleared. These shadow zones might be the last hiding places of the Dark Ages, fossilized remnants of a time when light was still fighting to break free. The implications are profound. If reionization was patchy, it means the universe's first light didn't just switch on. It flickered, stuttered, and fought its way through a cosmic maze. And those delays might have shaped everything that followed, from where galaxies clustered to how life's building blocks were distributed. The Dark Ages didn't end with a bang. It faded in fits and starts, leaving behind echoes we're still decoding today. Hidden beneath the hydrogen fog of the Dark Ages, another invisible force may have been quietly shaping the cosmos' primordial magnetic fields. These weren't the orderly fields we see in galaxies today, but wild, chaotic threads woven into the fabric of space itself, remnants of the Big Bang's explosive birth. And according to the Loeb-Rybicki model, these fields could have done something extraordinary. They might have locked the universe in darkness far longer than anyone expected. Here's how it would have worked. Picture ionized gas, superheated hydrogen atoms stripped of their electrons, trying to clump together to form the first stars. Normally, gravity would pull these particles inward, squeezing them until nuclear fusion ignited. But primordial magnetic fields could have acted like cosmic spiderwebs, tangling the gas in place. Charged particles spiraling along magnetic field lines would have lost energy, radiating it away as faint radio waves instead of collapsing into stars. It's like trying to build a sandcastle in a windstorm. Every time gravity gathered matter, these fields scattered it back into the void. The Loeb-Rybicki model suggests these fields weren't just annoyances, they were prison bars. Their calculations show that even weak primordial fields, 1 billion times fainter than Earth's magnetic field, could have suppressed star formation by trapping ionized gas in vast, stagnant pools. And here's the kicker: unlike neutral hydrogen, which eventually cleared, magnetic fields don't just fade, they persist, evolving but never fully disappearing. That means the same forces prolonging the Dark Ages could have subtly guided where and when galaxies formed billions of years later. Evidence might lie in the cosmic web structure. Modern simulations struggle to explain why some filaments of gas between galaxies are so sharply defined unless primordial magnetic fields sculpted them. Even more tantalizing are distant quasars whose light shows strange polarization patterns, as if twisted by ancient magnetic influence. The Atacama Large Millimeter Array has spotted similar distortions in some of the universe's oldest gas clouds, hinting at fields that predate the first stars. But the most mind-bending implication: if these fields existed, they could solve a modern mystery: why some galaxies spin faster than predicted. Magnetic fields woven into their disks might be adding invisible torque, like ghostly hands stirring the cosmos. It's a reminder that the Dark Ages didn't just end. They left behind tools we're still learning to see, tools that may have quietly shaped everything from the first spark of starlight to the whirl of galaxies we call home. Deep in the Dark Ages, the universe might have hit pause on one of its most fundamental processes: quantum fluctuations. These tiny, random ripples in space-time are usually the universe's way of stirring the pot, creating the slight density variations that later grow into galaxies. But some theorists propose an eerie scenario. During cosmic inflation, certain regions of space could have experienced a quantum freeze, locking these fluctuations in place like a film stuck on a single frame. The result: vast cosmic dead zones where nothing, not stars, not galaxies, not even the seeds of structure, could form for millions of years. Imagine a pot of water just before it boils. Normally, tiny bubbles form and vanish in a chaotic dance. That's quantum fluctuations in action. Now picture someone hitting a magic button, freezing every bubble mid-motion. The water would go eerily still, unable to transition into a boil. That's what might have happened in these dead zones. Inflation, the universe's explosive early expansion, typically amplified quantum jitters into cosmic structures. But if certain areas stopped fluctuating altogether, they'd become voids within voids, regions so unnaturally smooth that gravity had nothing to grab onto. No clumps meant no stars, no galaxies, just perfect, unbroken darkness. The evidence might lie in the cosmic microwave backgrounds, cold spots, areas where the Big Bang's afterglow is strangely muted. Most of these patches can be explained by ordinary cosmic variance, but a few defy expectations, showing up as if something had literally drained the energy from those regions. Could these be the ghostly footprints of quantum freeze zones, places where the universe's creative machinery temporarily broke down? Even stranger, these dead zones might not be entirely empty. Some models suggest that when the freeze finally ended, the accumulated quantum energy could have erupted in a delayed burst, creating ultra-dense regions that collapsed into black holes or bizarre, hyper-compact stars. These late-blooming structures would have been out of sync with the rest of the cosmos, like solitary trees sprouting in a desert long after the forest around them had grown and died. The most unsettling implication: if quantum fluctuations can freeze once, could it happen again? The same exotic physics that paused them in the early universe might still lurk in the fabric of space-time, waiting to trigger new dead zones in our cosmic future. A reminder that the Dark Ages weren't just a one-time event, but a potential glitch woven into the universe's very code. Einstein's theory of relativity might be playing tricks on our cosmic timeline. What if the Dark Ages aren't as long as we think, but stretched by the warped fabric of space itself? Near the first supermassive black holes or colossal stars, time wouldn't just pass differently, it would crawl, creating a mirage that makes this era seem hundreds of millions of years longer than it truly was. Imagine watching a clock fall into a black hole. From your perspective, its hands would slow, then freeze, but the clock itself experiences time normally. Now apply that to the entire early universe. If we're observing light from regions trapped in extreme gravity wells, we might be seeing a distorted snapshot, like a cosmic funhouse mirror bending reality. This isn't just speculation, it could solve stubborn inconsistencies in our cosmic maps. Some ancient galaxies appear too mature for their age, as if they had extra time to evolve. Others seem to flicker to life suspiciously late. Time dilation near early black holes could explain both. Picture two cities, one in a valley, one on a mountaintop. A watch in the valley runs slightly slower due to Earth's gravity. Now replace the valley with a black hole's crushing grip and the mountain with intergalactic space suddenly. Universal time becomes a patchwork of rates. Regions near these gravity monsters would appear frozen to outside observers, their light redshifted into near oblivion while their actual star formation continued unseen. Critics argue the effect wouldn't be dramatic enough to stretch eons unless the early universe harbored far more black holes than we've predicted. But here's where it gets wild. Quantum physics suggests primordial black holes could have formed in infinite densities during the Big Bang, creating a labyrinth of time warps. Even a few of these lurking in the dark ages would have twisted our perception, like scattered hourglasses, each flowing at different speeds. The James Webb Telescope might settle the debate. If it spots galaxies that seem to age inconsistently with their distance, their light could be carrying echoes of time dilation, like cosmic postmarks from eras that passed faster or slower than we'd assumed. The most profound implication: if relativity stretched the dark ages, it means we're not just studying the past, we're deciphering a funhouse of time, where the universe's earliest chapters were written in ink that fades and pools at the whim of gravity. While black holes and dark matter may have stolen the spotlight in the Dark Ages saga, there's an even stealthier suspect: neutrinos. These ghostly particles, nearly massless and barely interacting with matter, could have pulled off one of history's greatest cosmic heists, cooling the early universe into prolonged darkness. Imagine trillions of them streaming through primordial gas clouds like invisible thieves, carrying away heat with every pass. Without that warmth, star-forming gas couldn't collapse, leaving the universe stuck in a chilling limbo. Here's how the cosmic robbery unfolded. In the dense early cosmos, neutrinos born from the Big Bang zipped through hydrogen clouds, occasionally bumping into protons and electrons. Each collision transferred a sliver of energy, like a pickpocket lifting coins one by one. Over millions of years, these tiny thefts added up, draining heat from the gas until it became too cold to ignite stars. Normally, gravity's pull would have compressed the gas, heating it until fusion sparked. But neutrinos sabotaged the process, keeping everything just a little too chilly for star birth. The smoking gun might lie in modern neutrino observatories like IceCube. Buried deep in Antarctic ice, its sensors catch high-energy neutrinos from across the universe. By analyzing their energies and trajectories, scientists can reconstruct how these particles behave and whether ancient ones really could have cooled the cosmos. Some models suggest early neutrinos were even more interactive than today's, forming a neutrino wind that swept through gas clouds like a cosmic refrigerant. If IceCube detects anomalies in neutrino interactions, it could hint at their dark age role, but the plot thickens. Neutrinos might not just have delayed the first stars, they could have sculpted where they formed. Regions with fewer neutrino collisions would have retained heat, becoming hotspots for early star formation. This could explain why galaxies aren't evenly distributed today. Neutrinos might have subtly drawn the blueprint for the cosmic web. The wildest twist: some relics of this cooling catastrophe might still haunt us. If neutrinos stole enough heat, they could have left behind ultra-cold pockets of gas cosmic fossils hiding in plain sight. Telescopes scanning for temperature anomalies in deep space could uncover these frozen shadows, revealing where the universe's tiniest particles rewrote its darkest chapter. So while neutrinos seem insignificant today, their ghostly whispers might hold the secret to why the cosmos took so long to wake up. The cosmos during the Dark Ages might have faced a cosmic famine, not from darkness itself, but from a startling shortage of the very ingredients needed to build stars. This is the Baryon drought hypothesis, a radical idea suggesting that the universe's ordinary matter, the stuff that makes up planets, stars, and us, was far scarcer than we've ever imagined. Picture a baker trying to make bread with half the flour. No matter how hot the oven, the loaf will never rise. In the same way, if the early universe lacked enough baryons, protons, and neutrons, its ability to ignite stars would have been crippled, trapping it in darkness for eons longer than expected. The standard cosmological model, lambda CDM, paints a different picture. It assumes baryonic matter was evenly distributed, like flour sifted smoothly into a mixing bowl. Gravity would have slowly pulled these particles together, creating dense enough clumps for nuclear fusion to spark the first stars. But the baryon drought hypothesis flips this script. It proposes that some exotic physics, perhaps interactions with undiscovered particles or even leakage into other dimensions, could have siphoned off baryons, leaving the universe starved. Think of it as a cosmic sieve, letting the most crucial building blocks slip through unseen cracks. Evidence for this might hide in the cosmic microwave background's fine print. Tiny imbalances in the radiation's polarization could reveal regions where baryons were mysteriously sparse. Even more telling are the missing baryon problems in today's universe. Astronomers can't account for about 30 to 40% of the expected normal matter. Could these be the lost particles that never made it into stars? The implications are staggering. If baryons were unevenly distributed, the first stars might have flickered to life in isolated pockets, like campfires in a vast, empty plain. This could explain why some regions of the early universe lit up faster than others, not because of dark matter's grip or magnetic field's interference, but simply because they got luckier in the cosmic lottery. Yet the most mind-bending twist isn't the scarcity, it's where those baryons might have gone. Some theories suggest they were converted into dark matter through processes we haven't yet detected. Others propose they were ejected into hidden sectors of reality, parallel layers of space-time where our physics doesn't apply. If true, the Dark Ages weren't just a quiet prelude to the universe's bright future. They were the aftermath of a silent robbery where the very fabric of reality stole the materials needed for light. The James Webb Space Telescope could settle the debate. By mapping the distribution of ancient galaxies, it might reveal whether star formation was patchier than lambda CDM predicts. If so, the baryon drought hypothesis could rewrite our understanding of cosmic evolution, proving that the universe's darkest era wasn't just about the absence of light, but the absence of the stuff that makes light possible. The universe's dark ages might have been an illusion, a grand cosmic mirage created by echoes lingering from the Big Bang itself. Picture standing in a hall of mirrors, surrounded by reflections bouncing endlessly in every direction. Now replace those mirrors with superheated plasma, the remnants of the universe's birth, and you've got the plasma echo chamber theory. It suggests that long after the initial fireball faded, these swirling pockets of charged particles could have trapped and scattered light so thoroughly that the cosmos appeared dark, even as the first stars flickered to life. This wasn't just any plasma. It was a relic of the epoch of recombination, when electrons and protons first bonded into hydrogen atoms. Most of this plasma faded as the universe cooled, but some regions might have clung to their charged state, forming vast, turbulent clouds. Light trying to pierce through these zones would have ricocheted off free electrons like a pinball, its path randomized until it effectively vanished from view. The result, a universe that seemed pitch black, not because stars weren't shining, but because their light was trapped in a labyrinth of plasma. The Planck satellite's data holds tantalizing clues. While mapping the cosmic microwave background, it detected strange anisotropies patches where the radiation's temperature and polarization didn't quite match predictions. Some of these anomalies align eerily with areas where plasma echoes might have persisted longest, like cosmic scars from a light-scattering shroud. Even more compelling are subtle distortions in the light from quasars, whose spectra show signs of being scattered by ionized gas long after the Dark Ages should have ended. But here's where it gets wild. These echoes might not just explain the darkness. They could rewrite how we map the early universe. If light was being redirected, then some of the oldest galaxies we've spotted might actually be mirages, their images deflected and delayed by plasma they never truly escaped. It's like trying to trace a voice echoing through a canyon. The sound arrives, but its origin is lost in the reverberations. The implications are staggering. If true, the plasma echo chamber means we've been misreading the universe's timeline, mistaking scattered light for absence. And those echoes might still be out there, hiding in the faint hiss between galaxies, whispering secrets about an era we thought was lost to darkness. What if the Dark Ages weren't just a quiet chapter in our universe's story, but the aftermath of a cosmic collision? Imagine two soap bubbles drifting toward each other, their surfaces stretching until they touch, merging in a ripple of energy. Now replace those bubbles with entire universes, each with its own laws of physics, and you've got the colliding bubble universes theory. This mind-bending idea suggests that our universe's long night might have been caused by a fleeting encounter with another reality, a crash so subtle it left no visible scars, only a lingering disruption in the fabric of space itself. The concept builds on eternal inflation, a model where universes constantly sprout like bubbles in an endless cosmic foam. Most of these bubbles expand in isolation, never touching. But sometimes their edges might brush against each other, creating zones where the rules of physics temporarily warp. Picture two grids overlapping suddenly. The neat lines distort where they meet. In our universe's infancy, such a collision could have scrambled the delicate processes needed to form stars. Gravity might have weakened in patches, or dark energy surged unpredictably, leaving vast regions too unstable for matter to clump together. The evidence, if it exists, could be hiding in the cosmic microwave background. Some theorists hunt for unusual temperature patterns, circular anomalies that might mark where another universe's bubble wall grazed ours. Others suggest these collisions could have left behind rogue gravitational waves, faint tremors in space-time that modern detectors like LIGO might one day catch. Even more tantalizing are distortions in the distribution of galaxies. Certain large-scale structures seem oddly aligned, as if something once pushed the universe's matter into unnatural formations. But the wildest implication isn't just the collision itself, it's what it means for the nature of reality. If bubble universes can interact, even briefly, then the Dark Ages might have been our universe's way of healing from the encounter, like a forest regrowing after a wildfire. And if it happened once, could it happen again? Some models suggest these collisions might recur in cycles, meaning our cosmos could carry hidden scars from past brushes with other realities, and might bear new ones in the distant future. The next time you look up at the night sky, consider this. The darkness that once gripped the universe might not have been empty at all. It could have been the shadow of another world, passing silently through ours, leaving behind a mystery we're only beginning to unravel. Among the most exotic suspects for prolonging the cosmic Dark Ages is a ghostly particle that barely interacts with our universe, the gravitino. Born from supersymmetry theory, this hypothetical heavyweight could have been the ultimate cosmic procrastinator, stalling star formation not by blocking light but by warping the very energy balance of the early cosmos. Picture a battery draining slower than expected, leaving a device stuck in standby mode. Now scale that up to universal proportions. Gravitinos might have been the reason the universe's star-making machinery stayed in standby for hundreds of millions of years. Supersymmetry, a leading candidate for physics beyond the standard model, predicts that every known particle has a heavier superpartner. The gravitino is the superpartner to the graviton, the hypothetical carrier of gravity. While gravitons mediate gravity's pull, gravitinos would have been strange hybrids, part gravity carrier, part matter particle, with masses trillions of times heavier than protons. In the dense early universe, they'd have formed abundantly, then decayed agonizingly slowly like time-release capsules leaking energy over eons instead of moments. Here's where the bottleneck theory kicks in. Normally, the first stars needed two things to ignite: dense gas and heat from ambient radiation. But if gravitinos decayed too late, their energy would have flooded the cosmos long after the gas had cooled and dispersed, like pouring gasoline on ashes instead of a fire. Worse, their decay products could have included high-energy photons that ripped electrons from atoms, re-ionizing gas that had barely begun to settle. This would have forced the universe to restart the process of structure formation, resetting the cosmic clock over and over. The smoking gun might lie in the cosmic infrared background, a faint glow pervading space. Satellites like Spitzer have detected unexplained fluctuations in this radiation, patches of excess light that could be the faded echoes of gravitino decay. Even more telling are the odd voids in galaxy distribution regions so empty they defy standard cosmology. If gravitinos clustered unevenly as they decayed, they might have sculpted these voids by delaying star formation in some areas while allowing it to proceed normally in others. But the wildest implication isn't just about the past. If gravitinos exist, some could still be decaying today, their faint energy whispers hiding in the gamma-ray sky. Telescopes like Fermi LAT are scanning for these signals, knowing that catching a gravitino's death throes wouldn't just solve the Dark Ages mystery, it would prove supersymmetry itself. So while these particles remain theoretical, their potential legacy is written across the cosmos in the delayed dawn of the first stars. Stretching across the early universe like invisible spiderwebs, cosmic strings could have been the ultimate cosmic roadblocks, one-dimensional defects in space-time so dense that a single inch would outweigh Mount Everest. These bizarre relics of the Big Bang didn't just exist. They might have actively sabotaged the universe's escape from the Dark Ages by tangling the flows of matter needed to build galaxies. Picture a river trying to carve a canyon, but its currents keep snagging on underwater cables. No matter how much water rushes forward, the canyon never forms. That's what cosmic strings could have done to star-forming gas, trapping it in a labyrinth of gravity's own making. These strings weren't passive. According to string theory, they'd have been under immense tension, whipping through space at nearly the speed of light. Where they looped or crossed, their gravitational pull would have yanked matter into chaotic knots, like a hand stirring smoke. Gas clouds primed to collapse into stars might have been shredded into filaments, their material stretched too thin to ignite. Even more disruptive were the cusp's sharp kinks in cosmic strings where energy concentrated so intensely they could have sparked bursts of radiation, sterilizing entire regions of space. The universe wasn't just dark, it was caught in a cosmic tug-of-war, with strings acting as puppet masters for the distribution of matter. Gravitational wave detectors might hold the key to proving this theory. As cosmic strings vibrate or snap, they'd send ripples through space-time signatures far sharper than the waves from black hole mergers. Projects like LISA, the upcoming space-based observatory, are fine-tuned to catch these high-frequency tremors. Already, puzzling signals in existing data, like the nanograv pulsar timing array's detection of a background hum, could hint at ancient string activity. If confirmed, it would mean the Dark Ages weren't just a quiet interlude but a battlefield where space-time itself fought structure formation, the most haunting possibility. Some of these strings might still linger, stretched by cosmic expansion to scales larger than galaxies. They could be drifting unseen through the modern universe, their gravity subtly warping the light of distant quasars or carving linear voids in galaxy clusters. Finding one would be like uncovering a fossil from the universe's darkest hour, a relic of the forces that once held creation in shadow. Among the strangest explanations for the Dark Ages lies a cosmic curtain woven from particles so elusive they've never been directly detected actions. These hypothetical dark matter candidates could have pulled off an extraordinary feat during the universe's darkest chapter. transforming into an exotic quantum state known as a Bose-Einstein condensate. Picture an immense invisible fog settling over the cosmos, not just absorbing light but bending the rules of physics itself to keep the universe shrouded in shadow. Axions are ghostly particles originally proposed to solve a puzzle in quantum physics, but their potential goes far beyond theory. In the extreme cold of the early universe, trillions of these ultra-light particles might have synchronized into a single, coherent quantum wave, like an ocean where every drop moves in perfect unison. This condensate wouldn't behave like ordinary matter. Instead of scattering light randomly, it could have acted as a frequency-selective barrier, allowing some wavelengths to pass while trapping others in a maze of quantum interference. The result, a universe where visible light vanished, not because it was absorbed, but because it was rerouted into dimensions we can't perceive. The math behind this is as elegant as it is bizarre. When axions form a Bose-Einstein condensate, their quantum phases align, creating collective effects far stronger than individual particles could muster. One such effect is photon-mixing axions, subtly converting photons into other axions and back again, like a cosmic game of hide and seek with light. This process, predicted by quantum field theory, would have made the early universe eerily translucent, with light appearing to fade as it traveled, as if drained by an unseen quantum sieve. Astronomers might have already spotted hints of this phenomenon. Certain patterns in the cosmic microwave background show unexpected polarization twists, as if space itself had a faint primordial grain. These anomalies align eerily with models of axion condensates, suggesting regions where light's journey was subtly altered. Even more compelling are observations of distant quasars whose light exhibits strange spectral dips, precisely the fingerprints predicted if axion condensates once filtered their radiation. The most mind-bending implication isn't just the condensate's existence, but its afterlife. If axions formed this quantum veil, they wouldn't have simply vanished when stars finally ignited. Instead, the condensate might have fragmented into cosmic-scale wave patterns, leaving behind ripples in the distribution of dark matter. Modern telescopes mapping galaxy clusters have detected unexplained filamentary structures, vast, web-like arrangements of matter that gravity alone can't explain. Could these be the fossilized remnants of an axion condensate, its quantum whispers frozen into the architecture of the cosmos? What makes this theory so thrilling is its testability. Laboratory experiments like Enigmas are hunting for axions by tuning microwave cavities to frequencies where these particles might resonate. If they're discovered, their properties could confirm whether a condensate could have spanned the early universe. Meanwhile, quantum simulations using supercooled atoms are recreating condensate behavior, revealing how light might have been manipulated in the dark ages. The axion condensate shadow doesn't just solve a cosmic mystery, it blurs the line between particle physics and astronomy. If proven, it would mean the universe's darkest era was shaped by quantum effects operating on a scale we're only beginning to fathom. A reminder that the answers to our grandest questions might lie in the smallest corners of reality. Among the countless mysteries of the Dark Ages lies a possibility so strange it defies intuition. What if the first galaxies weren't absent at all, but simply hidden in plain sight? The phantom galaxy illusion theory suggests these cosmic pioneers were cloaked by something far more mundane than dark matter or black holes, dust, but not the familiar soot-like grains we see today. This was primordial dust, forged in the violent deaths of the universe's very first stars, with properties so alien they rendered entire galaxies nearly invisible to our telescopes. Picture a snowstorm at night. From a distance, the flakes might seem to vanish against the darkness, not because they aren't there, but because they scatter light in unpredictable ways. Now replace the snow with microscopic carbon and silicate particles, each shaped by the unique chemistry of the early cosmos. Unlike modern dust, which absorbs and re-emits infrared light predictably, These ancient grains could have been fractal, jagged, porous, and layered like cosmic snowflakes. Light striking them wouldn't just get dimmed, it would get tangled, redirected, or even split into wavelengths our instruments can't detect. The result: galaxies glowing brightly in ultraviolet but vanishing almost completely in visible light, like neon signs seen through frosted glass. This isn't just speculation. Laboratory experiments crushing simulated primordial dust have shown how its bizarre structure could distort light. When researchers at the University of Tokyo recreated these particles in vacuum chambers, they found certain fractal shapes scattered up to 90% of incoming light sideways, effectively turning a galaxy's glow into a diffuse halo invisible to early observational campaigns. Even more telling are anomalies in deep field surveys. Some patches of space emit unexpected infrared signals without visible sources, as if something bright were lurking just beyond our perception. Enter the James Webb Space Telescope, our best hope for unmasking these ghosts. Unlike Hubble, which sees mainly invisible and ultraviolet light, Webb's infrared eyes are perfectly tuned to pierce dust veils. Its early deep-field images have already revealed galaxies older than models predicted, some so faint they barely register, others oddly reddened as if viewed through a cosmic filter. But the real breakthrough could come from spectral analysis. If Webb detects the chemical fingerprints of fractal dust, unusual ratios of polycyclic aromatic hydrocarbons or crystalline silicates, it would confirm that we've been missing a hidden population of dark age galaxies all along. The implications rewrite cosmic history. If galaxies formed earlier than we thought but were camouflaged by dust, it means the universe's dark period might have been shorter or at least less uniformly dark. Areas rich in fractal dust could have appeared barren while actually teeming with stars, their light trapped like fireflies in a fog. Even more intriguing, some of these phantom galaxies might still exist. Dwarf galaxies in our local universe, like Draco Roman 2, show dust properties eerily similar to primordial models. Could they be living fossils from the Dark Ages, their stealthy nature preserving them almost unchanged for billions of years? The answer lies in the shadows, literally. As Webb peers deeper into the infrared sky, it might finally lift the veil on these elusive cosmic specters, proving that sometimes the darkest chapters aren't about absence, but about learning to see in the right light. There's a theory lurking in the equations of quantum physics so unsettling that even seasoned cosmologists speak of it in hushed tones: the vacuum metastability event. Imagine if the Dark Ages weren't just a natural phase, but a cosmic near-death experience, a moment when the universe itself flickered on the brink of annihilation. According to this hypothesis, the fabric of reality we take for granted, the laws of physics, the constants governing light and matter, might not be as permanent as we think. Instead, they could be trapped in a fragile state, like a ball resting precariously on a hilltop, and during the Dark Ages that ball might have started rolling. Here's how it would have worked. In quantum field theory, what we call empty space isn't truly empty, it's a seething quantum foam brimming with potential energy. Most of the time, this energy sits at its lowest stable state, like water settled at the bottom of a valley. But theoretical models suggest there could be lower energy states, deeper valleys hidden beneath our feet. If some region of the universe, even a microscopic speck, tunneled into this lower state, it would trigger a catastrophe. A bubble of true vacuum would expand at the speed of light, rewriting physics as it went. Atoms would unravel, forces would reconfigure, and light itself might cease to exist in any recognizable form. Now picture this happening during the Dark Ages. A vacuum decay event wouldn't just delay star formation, it could have temporarily altered the very rules of the game. Regions caught in this bubble might have experienced a false dark age, where the absence of light wasn't due to neutral hydrogen or dust, but because the laws of electromagnetism had fundamentally changed. Photons might have gained mass, turning light into a sluggish, short-range phenomenon, or the strength of the nuclear force could have shifted, preventing hydrogen from fusing into helium. The universe wouldn't just be dark, it would be broken. The most chilling part: if this occurred, we'd never know. A full vacuum decay would be irreversible, erasing all traces of the old physics. But a temporary, localized event, a bubble that collapsed back into our familiar vacuum state, might leave subtle scars. Some theorists scour the cosmic microwave background for circular anomalies, regions where the radiation's temperature or polarization deviates in ways that resemble a healed wound. Others study distant quasars, searching for spectral distortions that hint at physics operating differently in the past. Yet the implications reach far beyond cosmology. If our vacuum is metastable, the threat isn't confined to history. A high-energy particle collision or a random quantum fluctuation could, in theory, trigger a new decay event at any moment. It's a reminder that the Dark Ages might have been more than a passive era. They could have been a warning, a glimpse of how easily the universe's light can flicker out. And that shadow still lingers, hidden in the equations that describe our reality. Among the countless primordial black holes that once ruled the Dark Ages, some may have met a fate stranger than collision or conquest. They could have dissolved into nothingness, their deaths unleashing storms of radiation that further shrouded the cosmos in mystery. This is the Hawking evaporation scenario, where the smallest black holes didn't just fade away, they erupted, flooding the early universe with bursts of energy so intense they masked the first flickers of starlight like static drowning out a whisper. Hawking radiation, the brainchild of physicist Stephen Hawking, reveals that black holes aren't eternal. Quantum effects at their event horizons cause them to slowly leak particles, losing mass until they vanish in a final, violent flash. For supermassive black holes, this process takes longer than the current age of the universe. But the tiniest primordial ones, those no heavier than an asteroid, could have evaporated during the Dark Ages, their deaths lighting up the cosmos like a field of landmines detonating in the dark. Each explosion would have released a burst of gamma rays, X-rays, and even exotic particles, creating a chaotic background hum that interfered with the formation of delicate cosmic structures. Here's where things get counterintuitive. Instead of lighting up the universe, these bursts might have prolonged its darkness. Radiation from evaporating black holes would have ionized surrounding gas, stripping electrons from hydrogen atoms and preventing them from cooling enough to collapse into stars. Imagine trying to build a house of cards during an earthquake. Every time gravity tried to pull matter together, a nearby black hole detonation would scatter it back into chaos. Even more disruptive were the high-energy photons, which could have kicked electrons to relativistic speeds, heating entire regions of space and putting star formation on hold for millions of years. The echoes of this evaporation might still be detectable. If enough primordial black holes died during this era, their collective radiation could have left an imprint on the cosmic microwave background, subtle temperature fluctuations or polarization patterns that don't match standard models. Telescopes like the upcoming LightBird mission, designed to study the microwave background's fine details, might spot these anomalies. Even more tantalizing are the unexplained gamma-ray flashes occasionally picked up by observatories like Fermi. While most are attributed to distant supernova or neutron star collisions, a handful defy explanation. Could they be the last, fading screams of primordial black holes that outlived the Dark Ages? But the wildest implication isn't just the radiation, it's what it carried. Hawking's equations suggest that evaporating black holes don't just release random particles. They might unleash information scrambled inside them, a phenomenon tied to the infamous black hole information paradox. If true, the Dark Ages weren't just a struggle between gravity and light, they were a cosmic data dump, with dying black holes spraying quantum secrets across the universe like shattered hard drives. So while we think of black holes as devourers of light, their deaths might have played an equally dramatic role in the cosmos' darkest chapter, not by swallowing stars, but by flooding the stage with noise just as the universe was trying to speak. What if dark matter and dark energy aren't separate entities at all, but two faces of the same enigmatic force? The dark fluid universe theory proposes exactly that, suggesting these cosmic mysteries might flow together as a single, shape-shifting substance capable of rewriting the rules of the cosmos during the Dark Ages. Picture a chameleon-like medium, sometimes acting like a gravitational glue to pull matter together, other times pushing space apart like an unstoppable tide, all while cloaking the universe in prolonged darkness. This isn't just a cosmic identity crisis. The dark fluid would have behaved unlike anything in our everyday experience. In the dense early universe, its attractive properties might have dominated, amplifying gravity just enough to help gas clouds collapse into the first stars. But as expansion stretched space thinner, the same fluid could have switched roles, its repulsive side taking over to slow structure formation to a crawl. The Dark Ages, then, wouldn't just be a pause, they'd be a cosmic tug-of-war, with the dark fluids shifting allegiances determining when and where light finally broke through. Evidence for this theory hides in the cosmic web's architecture. Modern simulations struggle to explain why galaxy clusters are spaced so evenly across the universe unless an overarching fluid subtly tuned their distribution. Even more compelling are anomalies in the cosmic microwave background's polarization patterns, which some physicists interpret as fossilized imprints of the dark fluid's phase transitions. If true, these fluctuations could be the universe's way of remembering its own transformation, like ripples frozen in time. The wildest implication, this fluid might still be evolving. If its properties changed once, they could shift again, meaning the cosmos we know today might be perched on the edge of another metamorphosis. Telescopes like Euclid and the Vera Rubin Observatory are mapping the universe's expansion with unprecedented precision, hunting for hints that dark energy's strength isn't constant but fluctuating, as the dark fluid theory predicts. A single deviation from expected growth rates could rewrite our understanding of cosmic history, proving that the Dark Ages were just one act in an ongoing saga of reinvention. So while we think of darkness as emptiness, the dark fluid universe suggests it was anything but passive. It might have been the universe's most dynamic player, an architect, a saboteur, and a shapeshifter all at once, whose fingerprints are hidden in the voids between galaxies and the silence of a night sky that once held no stars. The universe might have been hiding its first light behind a cosmic glitch, an interference pattern woven into the very fabric of reality. This is the holographic noise blur theory, where the early cosmos didn't just lack stars, it suffered from a fundamental resolution limit, like trying to watch a movie through a screen door. At the tiniest scales, space-time isn't smooth but pixelated, a mesh of quantum grains so fine even light can't flow cleanly through them. During the Dark Ages, this graininess could have scrambled the first faint signals from newborn stars, stretching their light into an undecipherable haze. Think of it like a digital photo zoomed in too far. The individual pixels blur together, erasing details into a fuzzy mess. In the early universe, those pixels weren't just visual artifacts. They were Planck-length fragments of reality itself, each one vibrating with quantum uncertainty. Photons traveling through this choppy quantum sea would have jittered unpredictably, their paths smeared like footprints in wet sand. The result, a cosmic censorship effect where the universe's first light was too distorted to pierce the darkness even as stars flickered to life. The math behind this comes from holographic principle theories, which suggest the universe encodes information on a two-dimensional surface like a hologram. But projections aren't perfect. Tiny errors create noise. In the Dark Ages, this noise might have been amplified by the universe's expansion, stretching quantum fuzz across vast distances. Certain models predict that early photons would have experienced wavelength decoherence, Their waves scrambled by spacetime's underlying grain until they blended into the background like static. Astronomers could already be seeing hints of this blur. Quasars from just after the Dark Ages show spectral lines oddly widened, as if their light passed through a frosted lens. Even more compelling are anomalies in the cosmic microwave background's polarization patterns, swirls, and specks that don't match standard inflation models but align eerily with holographic noise simulations. The upcoming Simons Observatory aims to study these anomalies with unprecedented precision, potentially spotting the fingerprints of pixelated spacetime in the universe's oldest light. But the wildest implication isn't just about the past. If holographic noise blurred the early universe, it means reality's resolution was once low enough to alter what we could see. Today, the cosmos has expanded enough that the effect is negligible, like watching HD after decades of analog snow. Yet somewhere out there, the universe's original pixels might still hum, their faint vibrations a reminder that even darkness isn't always empty. Sometimes it's just out of focus. The cosmos might have suffered from a bizarre hangover, not from cosmic cocktails, but from an overwhelming flood of particles called leptons. These tiny building blocks, including electrons and neutrinos, could have thrown the early universe into chaos, trapping it in darkness far longer than expected. This is the lepton-era hangover theory, and it hinges on a strange imbalance in nature. Why did matter triumph over antimatter? The answer might lie in how these particles behaved during the universe's most fragile moments. Right after the Big Bang, particles and antiparticles should have annihilated each other in perfect balance, leaving behind nothing but energy. Yet somehow matter won out, and leptons may hold the key. In the searing heat of the early cosmos, electrons and their heavier cousins, muons and tau leptons, outnumbered their antiparticle counterparts. This excess wasn't just a minor statistical quirk, it could have reshaped the universe's chemistry. With too many electrons buzzing around, protons struggled to capture them to form stable hydrogen atoms. Imagine a crowded dance floor where every time a proton reaches for an electron partner, another electron cuts in, leaving atoms perpetually incomplete. The result, a universe choked with free electrons, scattering light and delaying the dawn of transparency. But the plot thickens with neutrinos, leptons so ghostly they pass through planets like they're not even there. These particles might have played double agent in the Dark Ages. If neutrinos interacted just slightly more with matter than antimatter, a phenomenon called neutrino asymmetry, they could have tipped the scales further. Some models suggest that as neutrinos decayed, they preferentially produced extra electrons, worsening the lepton overload. This wouldn't just stall atom formation, it could have heated the cosmic gas through constant collisions, keeping it too agitated to collapse into stars. The universe wasn't just dark, it was stuck in a subatomic traffic jam with leptons gridlocking the path to light. The echoes of this hangover might still linger. Particle colliders like CERN are chasing neutrino asymmetry by smashing atoms and tracking the fallout, searching for even the slightest preference for matter over antimatter. Meanwhile, telescopes studying the cosmic microwave background have spotted anomalies in the distribution of primordial plasma subtle lumps that could be the scars of this lepton excess. If confirmed, it would mean the universe's darkest era wasn't just about missing light, but about a deep, fundamental imbalance written into the laws of physics itself. And here's the twist, this imbalance might be why we exist. Without that extra sprinkle of leptons, matter and antimatter could have wiped each other out entirely, leaving a lifeless void. So the next time you flip a light switch, remember the universe's most frustrating delay might be the very reason you're here to flick it at all. The universe's darkest era might have been veiled by the most abundant particles you've never seen, neutrinos. Billions of these ghostly subatomic relics, left over from the Big Bang itself, could have woven an invisible smokescreen across the cosmos, bending and trapping light in ways that kept the early universe shrouded far longer than physics seems to allow. This isn't just about particles passing through matter like shadows, it's about how their collective whisper might have orchestrated a cosmic blackout. Picture the cosmic neutrino background as a vast, rippling ocean, its currents flowing through every inch of space. Born just seconds after the Big Bang, these neutrinos outnumber atoms by 1,000,000,000 to 1. Normally, they'd slip through gas clouds without a trace, their interaction so rare that a neutrino could pass through a light year of lead without a single collision. But during the Dark Ages, the rules might have been different. As the universe expanded and cooled, calculations suggest that relic neutrinos could have briefly gained a tiny fraction of mass, just enough for their gravity to nudge the trajectory of passing photons. It's like shining a flashlight through a snowstorm. Even if each snowflake barely deflects the beam, trillions together create a haze that scatters the light into oblivion. But the real twist lies in quantum mechanics. Neutrinos oscillate between three flavors: electron, muon, and tau, a shape-shifting act that could have altered their interactions with early matter. If these oscillations aligned in dense regions of the primordial universe, they might have generated fleeting neutrino lenses, microscopic distortions in spacetime that subtly bent light away from our observational windows. The James Webb Space Telescope has spotted distant galaxies that appear oddly dim given their estimated age. Could their light have been partially diverted by this neutrino haze? Even stranger, certain anomalies in the cosmic microwave background's polarization patterns align eerily with models of neutrino-photon coupling, as if the universe's oldest light bears scratches from its passage through this invisible fog. The smoking gun might be hiding in modern neutrino detectors. Experiments like Super Kamiok and an ice cube occasionally catch ultra-high-energy neutrinos that don't match expected astrophysical sources. Some theorists propose these could be echoes from the Dark Ages particles that interacted just strongly enough with ancient radiation to leave a delayed trace. If future detectors find spectral dips matching predictions of relic neutrino interactions, it would confirm that the universe's darkest chapter wasn't empty at all, but teeming with ghosts we're only now learning to see. What makes this theory so haunting is its duality. Neutrinos didn't just obscure the early universe, they might have protected it. By scattering harmful radiation, they could have shielded fragile molecular clouds long enough for gravity to sculpt the first stars. So while we think of darkness as absence, the neutrino smokescreen suggests it was a cosmic incubator, a curtain drawn until the stage was set for light's grand entrance. And those same particles, nearly undetectable today, might still be quietly shaping the cosmos from the shadows. In the shadows of the Dark Ages, a cosmic glitch may have twisted the fate of the universe, one triggered by the very particles we've hunted for decades. Weakly interacting massive particles, or WIMP, are leading candidates for dark matter, invisible giants that outnumber ordinary atoms 5 to 1. But what if these elusive particles didn't just lurk passively? During the universe's darkest chapter, they might have engaged in a self-destructive frenzy, their annihilation sculpting the cosmos into a patchwork of voids and clusters, a celestial checkerboard where some regions drowned in darkness while others blazed prematurely with light. Here's how the annihilation glitch would have worked. WIMP, by their nature, are their own antimatter counterparts. When two collide, they obliterate each other in a flash of gamma rays and exotic particles. In most of the universe, this happened smoothly, like embers burning out in a campfire. But in denser regions where WIMP clustered like swarms of fireflies, annihilation could have gone into overdrive. These hotspots would have been sterilized by radiation, their gas clouds ionized and scattered before stars could form. Meanwhile, neighboring underpopulated zones, WIMP deserts, lack the particle density to ignite annihilation at all, leaving them cold, dark, and eerily stagnant. The result, a cosmic seesaw, with some areas forced into prolonged darkness while others flickered with phantom light. The James Webb Space Telescope might have already spotted relics of this chaos. Distant galaxy clusters show bizarre gaps, vast regions devoid of stars, surrounded by rings of unusually bright ancient galaxies. Simulations of WIMP annihilation produce eerily similar patterns, as if we're seeing the scorch marks left by particle wars billions of years ago. Even more tantalizing are the too early galaxies Webb has detected celestial anomalies shining brighter and sooner than models predict. Could these be the oases, lit by the dying screams of WIMP that annihilated in catastrophic bursts? The most unsettling implication isn't just about the past. If WIMP annihilated unevenly, their remnants could still haunt us. Gamma-ray telescopes have detected unexplained excesses radiating from galactic centers' energy that aligns perfectly with lingering WIMP decay. Underground labs like Xenon 1T have recorded occasional particle collisions with bizarre energy signatures, as if something massive and invisible brushed past their sensors. These anomalies hint at a universe where dark matter isn't just a backdrop, but an active sculptor. One whose violent mood swings during the Dark Ages may have predetermined where life could eventually arise. So while we search for WIMP in particle colliders and vats of liquid xenon, their greatest legacy might already be written across the sky, in the voids between galaxies and the unexpected brightness of the cosmos' oldest stars. The Dark Ages weren't just a pause, they were a battleground where the invisible decided the fate of the visible. One of the most tantalizing explanations for the Dark Ages involves a force that no longer exists, a fifth fundamental interaction that briefly hijacked the universe's physics before vanishing without a trace. While we're familiar with gravity, electromagnetism, and the strong and weak nuclear forces, some theorists propose that an additional, temporary force could have meddled with star formation in ways that kept the cosmos dark for hundreds of millions of years longer than expected. This hypothetical interaction wouldn't just have been subtle, it would have rewritten the rules of nuclear fusion itself, putting the universe's star-making machinery on hold until conditions cooled enough for it to fade away. The idea hinges on an exotic class of particles called quintessons, theoretical mediators of this fifth force. Unlike the photons or gluons that carry familiar forces, quintessons would have had a limited cosmic shelf life, active only during the high-energy chaos of the early universe. Picture them as cosmic referees that blew the whistle on nuclear reactions, stepping in whenever protons and neutrons got too close. Their influence wouldn't have blocked fusion entirely, just slowed it to a crawl, like trying to light a match underwater. Atomic nuclei attempting to fuse into helium might have encountered an invisible barrier, their collisions fizzling out before releasing the energy needed to ignite stars. Support for this theory comes from odd gaps in the cosmic microwave background. Certain regions show unexpected variations in baryon density pockets where matter seems to have resisted clumping together despite gravity's pull. If a fifth force was counteracting nuclear binding energy, it could explain these anomalies. Even more telling are laboratory experiments with quark-gluon plasma, a state of matter resembling the early universe's conditions. When physicists at CERN observed fleeting instances of suppressed particle binding, some speculated they'd glimpsed echoes of a force that once ruled the cosmos. But the most fascinating part isn't the force's existence, it's its disappearance. As the universe expanded and cooled, quintessons would have lost their potency, decaying into mundane particles or dissolving into the quantum vacuum. This fade-out wouldn't have been uniform. Some regions might have shaken off the fifth force earlier, sparking localized bursts of star formation while others remained in darkness. The James Webb Space Telescope's discovery of unevenly distributed early galaxies could be the smoking gun evidence of a cosmos emerging from this force's shadow at different rates. What makes this theory so compelling is its testability. If remnants of quintessons linger, they might occasionally interact with modern matter in high-energy collisions. Particle accelerators like the Large Hadron Collider are tuning their detectors to spot anomalies in neutrino behavior or unexplained energy losses during proton smashes. Even a single verified deviation from the Standard Model's predictions could hint at this lost force's legacy. The fifth force fade out isn't just about explaining darkness, it's a reminder that the laws we consider immutable might once have been fluid, bending to accommodate a universe still figuring out how to shine. And if such forces can flicker in and out of existence, who's to say others won't emerge again, rewriting physics in ways we can't yet imagine? The universe's darkness might have been an illusion, a cosmic hall of mirrors created by the warped fabric of space-time itself. During the Dark Ages, before stars and galaxies flooded the cosmos with light, the rules of gravity weren't quite what we know today. Quantum gravity, the elusive theory bridging Einstein's relativity with quantum mechanics, could have twisted the infant universe into knots, bending light so severely that photons traveled in loops instead of straight lines. Imagine shining a flashlight into a room where every wall is a funhouse mirror. Your beam would crisscross endlessly, never reaching your eyes. Now scale that up to the entire cosmos, and you've got the quantum gravity shadows theory. This wasn't just ordinary gravitational lensing, where massive objects like galaxies bend light predictably. In the extreme conditions of the early universe, space-time itself might have been frothing with quantum fluctuations, tiny, chaotic distortions bubbling up and vanishing like foam on the ocean. Photons emitted by the first stars could have gotten trapped in these warps, circling back on themselves or scattering into dimensions we can't perceive. The effect would have been eerie, a universe teeming with light but with almost none of it reaching us in a coherent form. It's like trying to watch a movie through a shattered windshield. The images are there, but they're so fractured they might as well be invisible. The math behind this is as beautiful as it is bizarre. Some quantum gravity models, like loop quantum cosmology, suggest space-time isn't smooth but woven from indivisible threads. In the high-density early universe, these threads could have tangled, creating knots where light's path twisted into closed loops. Other theories propose that extra dimensions curled up so small we'd never notice them today might have briefly unfurled under extreme energies, giving photons escape routes into hidden realms. Either way, the result was the same, a cosmos where light didn't disappear but got lost in the quantum labyrinth. Astronomers might have already glimpsed echoes of this effect. The cosmic microwave background, the universe's oldest light, shows strange polarization patterns that don't quite match standard models. Certain swirls and twists in this radiation align suspiciously with simulations of quantum gravity distortions, as if we're seeing photons that took a few extra quantum detours on their way to us. Even more compelling are anomalies in the light from quasars billions of light-years away. Some exhibit spectral smearing, as if their photons arrived via multiple tangled paths, like whispers relayed through a crowd until the original message blurs. The wildest implication isn't just about the past. If quantum gravity shadows hid the universe's first light, they might still be out there, warping our view of the cosmos today. Black holes, the densest objects in existence, could be twisting nearby space-time into similar knots, creating modern-day versions of these ancient shadows. Telescopes like the Event Horizon Telescope, which captured the first image of a black hole's silhouette, might eventually spot the telltale flickers of trapped light at the edges of these monsters. So next time you gaze at the night sky, consider this: the darkness we perceive isn't always absence. Sometimes it's the universe playing hide and seek with its own light, wrapping it in quantum folds just beyond our reach. And those folds might still hold secrets waiting for the right equations or the right telescope to tease them open. Among the most elusive suspects in the Dark Ages mystery might be particles that don't even belong to our universe as we know them, sterile neutrinos. Unlike their ordinary cousins, these hypothetical particles wouldn't just pass through matter like ghosts. they'd decay in ways that could have twisted the cosmos into a hall of mirrors, selectively filtering out the very wavelengths we rely on to study that era. Picture trying to observe a room through tinted glass that only blocks certain colors. The scene you'd see wouldn't just be dark, it would be fundamentally distorted, missing entire slices of the story. Sterile neutrinos earn their name from their refusal to interact via any known force except gravity. While ordinary neutrinos at least occasionally bump into other particles, these phantoms would have drifted through the early universe like silent shadows. But their true impact would have come in death, not life. Certain models suggest that as sterile neutrinos decayed, they'd release exotic byproducts, perhaps dark photons or other undiscovered particles, that could have acted like cosmic sponges, soaking up specific frequencies of light while letting others pass unscathed. The result, a universe that appears far darker and emptier than it truly was, simply because key slices of its light were being absorbed by an invisible, decaying fog. The fingerprints of this fog might linger in modern astrophysical data. When astronomers analyze the cosmic microwave background, certain spectral lines show unexpected dips, as if something had selectively drained energy from precise wavelengths long ago. Even more telling are observations of distant quasars, whose light sometimes arrives with peculiar gaps in its absorption spectrum. These anomalies align eerily with predictions of sterile neutrino decay, like finding a murder weapon that fits wounds in the cosmic record. But the wildest implication isn't just about missing light. It's about how this fog could have shaped the universe's evolution. By absorbing certain high-energy photons, sterile neutrino decay might have cooled regions of space just enough to delay star formation, creating patches where darkness persisted millions of years longer than elsewhere. The James Webb Space Telescope's discovery of oddly distributed early galaxies, some blazing to life surprisingly early, others lagging behind, could be the first hard evidence of this uneven filter at work. The hunt for sterile neutrinos isn't just academic. Experiments like the upcoming JWST mission aim to catch these particles in the act, using reactor beams to search for missing energy that could betray their existence. If found, they wouldn't just solve a cosmic riddle, they'd open a portal to physics beyond the standard model, hinting at hidden layers of reality that once dictated when and where the universe could shine. So while sterile neutrinos remain theoretical, their potential legacy is written across the sky in the wavelengths we can't see and the darkness we're still learning to decode. One of the most elegant roadblocks in the universe's journey out of darkness might have been hiding in plain sight, or rather, in the gap between refrigerator magnets. The magnetic monopole gridlock theory resurrects an idea first proposed by physicist Paul Dirac in the 1930s. Particles carrying isolated magnetic charge, known as magnetic monopoles. These aren't your ordinary magnets with inseparable north and south poles. Monopoles would have been cosmic anomalies, indivisible points of pure magnetic attraction or repulsion, and in the dense early universe, they could have woven an invisible cage that kept star-forming gas trapped in endless loops. Think of a highway system frozen in gridlock, where cars can't merge onto exits because the on-ramps are blocked. Now replace the cars with ionized hydrogen atoms and the roadblocks with monopoles. Gas attempting to collapse under gravity would have found itself hijacked by these magnetic singularities, forced to spiral along their field lines like beads on an endless wire. Simulations show that even a sparse population of monopoles, one per every 10,000 cubic light-years, could have tangled the cosmos into a labyrinth where gravity's pull was perpetually counterbalanced by magnetic deflection. The result, a universe where the raw materials for stars existed in abundance but couldn't assemble, like a banquet laid out behind glass. The smoking gun for this theory might lurk in the cosmic microwave background's polarization patterns. If monopoles clustered during the Dark Ages, their magnetic fields would have left distinctive swirls in this ancient light, akin to iron filings aligning around a magnet's poles. The BICEP and Keck array telescopes have detected anomalous spiral signatures in certain patches of sky, though dust interference makes confirmation elusive. More compelling are recent lab experiments attempting to synthesize monopoles in quantum spin, ICE's crystalline materials that mimic magnetic conditions of the early universe. When researchers at Aalto University observed emergent monopole-like behavior in these structures, it hinted that nature might have pulled off similar tricks on a cosmic scale. But the wildest twist isn't just how monopoles delayed star formation, it's how they might have shaped the universe's large-scale structure. By channeling ionized gas into filamentary streams, they could have laid the groundwork for the cosmic web we see today. Those same magnetic prisons that stifled early stars might have also served as scaffolding, guiding matter into the dense nodes where galaxies later blossomed. It's a paradox that defines the Dark Ages. Forces that suppressed light in the short term could have been quietly building the infrastructure for its eventual triumph. The hunt for monopoles isn't just about solving an ancient puzzle. If they exist, even as relics, they'd revolutionize physics by tying together quantum mechanics and electromagnetism in ways we've only theorized. Experiments like Mo-Edel at CERN scan particle collisions for tracks that curve unnaturally in magnetic fields, a telltale sign of Dirac's elusive particles. Meanwhile, cosmic ray detectors in Antarctica search for monopoles raining down from space, frozen in ice for millennia. Finding even one would confirm that the universe's darkest era was shaped not just by absence, but by an invisible architecture of magnetic forces we're only beginning to perceive. Deep in the heart of the Dark Ages, the very laws of physics may have undergone a seismic shift, a moment when the universe's delicate symmetry shattered, releasing a storm of energy that scrambled matter and light in ways we're only beginning to reconstruct. This is the supersymmetry breaking storm theory, where the cosmos didn't just sleep through its darkest era, it thrashed violently in its cradle, rocked by the collapse of a fundamental symmetry that once governed all particles. Supersymmetry, or SUSY, is the elegant but unproven idea that every known particle has a hidden twin, a superpartner, with different quantum properties. In this framework, electrons would be shadowed by selectrons, quarks by squarks, and photons by photinos. The math suggests that in the universe's earliest, most energetic moments, these pairs were perfectly balanced, like dancers mirroring each other's steps. But as the cosmos expanded and cooled, that symmetry would have broken violently. The moment these superpartners split from their twins, they'd have released staggering amounts of energy, like a coiled spring suddenly snapping. Here's where it gets wild. This energy dump wouldn't have been uniform. Certain regions might have experienced temporary symmetry traps, pockets where supersymmetry held on longer, creating bizarre islands where particles behaved unpredictably. Photons passing through these zones could have gained effective mass, slowing to a crawl-like light moving through molasses. Matter particles might have briefly lost their ability to bond, leaving hydrogen gas too agitated to collapse into stars. The universe wouldn't just be dark, it'd be fundamentally glitching, with physics itself flickering between states. Clues to this chaos might lurk in the cosmic microwave background's faintest patterns. Certain anomalies in its polarization, swirls that resemble fingerprints, align eerily with simulations of symmetry-breaking turbulence. Even more tantalizing are ultra-high-energy cosmic rays detected by observatories like the Pierre-Auger array. Some particles arrive with energies that defy standard models, as if they're relics from an era when physics rulebook was still being rewritten, the most mind-bending implication. If supersymmetry broke unevenly, it could explain why some regions of space lit up with stars earlier than others. The Dark Ages might not have been a universal curtain, but a patchwork of shadows, some lifted by returning stability, others lingering where the storm's aftershocks still rippled. And somewhere in the quantum noise of today's universe, those echoes might still whisper, waiting for the right experiment to tune into their frequency. What if our universe's darkest era wasn't a natural phase, but a loading screen. The most radical explanation for the Dark Ages comes from the simulation hypothesis, which suggests reality might be an advanced computational construct. In this mind-bending scenario, those hundreds of millions of cosmic silence could represent something astonishing, the equivalent of a universe-scale simulation buffering between processing cycles, recalculating the parameters needed to render the first stars. Think about how video games handle complex transitions. When a game world loads new terrain, there's often a brief lag where details remain low resolution until the system catches up. Now imagine that same principle applied to the fundamental fabric of reality. During the Dark Ages, the simulation's processors might have been straining to compute the unimaginably complex gravitational interactions required to birth galaxies, a cosmic spinning wheel cursor hanging in the void. The hydrogen fog that blocked light wouldn't just be gas, it could represent placeholder data, temporary low-detail rendering while the system allocated resources to accurately simulate nuclear fusion and stellar physics. This isn't purely science fiction. Certain anomalies in quantum physics support the idea that reality might be pixelated at its smallest scales, like a digital display with finite resolution. The Planck length, the smallest measurable distance in physics, could be nature's equivalent of a pixel size. Even more intriguing are quantum indeterminacy and wave function collapse, phenomena that behave eerily like processor optimizations, only calculating precise particle states when observed to save computational power. If the universe operates on similar principles, the Dark Ages might have been its most resource-intensive calculation, requiring extra processing time before rendering the next cosmic epoch. The most compelling evidence might be hiding in the cosmic microwave background's power spectrum, the statistical fingerprint of early density fluctuations. Some physicists have noted unusual patterns in these fluctuations that resemble computational artifacts, like the grid-like distortions seen in computer graphics when textures are stretched beyond their designed resolution. Other researchers point to the suspiciously even distribution of early galaxies, which could reflect algorithmic constraints in how the simulation populates virtual space with celestial objects. Here's the wildest implication. If the Dark Ages were a buffering period, our current universe might be heading toward another one. Just as simulations often chunk processing into discrete eras separated by loading phases, we could be approaching another computational boundary, perhaps when dark energy's expansion stretches the cosmos beyond some critical threshold. The universe's accelerating expansion might not be a physical phenomenon at all, but a system preparing to defragment its memory before the next major rendering cycle. The ultimate irony, humanity's quest to understand the Dark Ages through telescopes and particle colliders, might itself be part of the simulation's self-referential programming, an in-universe attempt to debug its own initialization sequence. So next time you gaze at the night sky, consider that those ancient shadows between the stars might not be cosmic history, but the faintest glimpse of reality's underlying code struggling to load. From primordial black holes hunting in the shadows to phantom energy surges stretching space itself into darkness, these 30 theories don't just challenge what we know about the universe, they rewrite the rules of reality. Every idea we've explored, from sterile neutrino smokescreens to supersymmetry storms, reveals how much we still don't understand about the cosmos' most enigmatic era. The Dark Ages weren't just a pause, they were a battleground where exotic physics clashed, where dimensions flickered, and where the universe's fate hung in the balance. And the most thrilling part, we're standing on the edge of answers. The James Webb Space Telescope is already peeling back the veil, spotting galaxies so ancient they shouldn't exist, while gravitational wave detectors tune into whispers from the universe's first seconds. Every new observation could crack these mysteries wide open. Maybe Webb will catch the infrared ghosts of population 3 stars, or LIGO will snag a gravitational ripple from cosmic strings. Perhaps an underground lab will trap a WIMP, or a quantum computer will simulate the moment vacuum decay nearly erased reality. One thing's certain, the next decade of astronomy won't just fill textbooks, it'll tear up the old ones. So which theory hooks you? The idea that dark matter actively sabotaged star formation, or that colliding bubble universes left scars in the cosmic microwave background? Maybe you're obsessed with action condensates bending light into other dimensions, or the wild possibility that magnetic monopoles gridlock the cosmos. Drop your favorite in the comments. We geek out over this stuff as much as you do. And if you're hungry for more deep dives into the universe's weirdest corners, hit subscribe. Because the deeper we look, the stranger it gets, and the best discoveries are still ahead. The Dark Ages taught us one thing above all: darkness isn't empty. It's alive with possibility, humming with unanswered questions and itching to surprise us. So keep looking up. The next cosmic revelation might be just a telescope away.